So before moving on to the Lewis definitions of acids and bases, I just want to point out that that interchangeable use of the term proton and H plus also makes its way into the way that we refer to certain chemical species. All right. So if I showed this particular chemical right here acting as a base where it's accepting a hydrogen, notice that once it accepts that hydrogen, it becomes this form right here. And often people will say that a base is in its deprotonated form before it accepts that hydrogen, and that it's in its protonated form after it accepts that. And again, it can be a little confusing because when you look at the difference between these two, I see a difference in hydrogens. All right, I don't necessarily see a proton in that, but the reason we use those terms is that this thing is accepting an H plus, and an H plus again is nothing but a proton. All right, so the last definition for acids and bases is the Lewis definition, and again I want to point out that this is part of the HL level, although they are fairly important in terms of the three definitions of acids and bases. So a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donator. And before I go on, I want to point out that it can be a little confusing because we've seen these terms acceptor and donator before. All right, we had donor or donator with the Bronsted-Lowry definitions, also acceptor. All right, and in this case, we did things more the way you traditionally think about donation or accepting. All right, traditionally, when you donate something, before you do your donating, you completely own the object, and after you're done, you don't have any possession of it at all. All right, but there's another way that we can think about the terms donating and accepting. All right, and I'm just going to use an example of a handshake. All right. When you are shaking somebody's hand, you could say, you are accepting that person's hand when you shake their hand, but in order to accept that person's hand, you have to donate your own hand. All right. So in this particular case, even though we use the term acceptor and donator, the person that's doing the donating does not actually lose possession of the thing that they're donating. All right. So so in this particular case, this would be the classic, a classic Lewis acid, Lewis base reaction. You're going to have this particular chemical, and what's going to happen is that the electron pair on this particular chemical can essentially make a bond between this atom and this atom right here. All right, and that's going to create one molecule. All right, and one thing that you're going to notice is that once this happens, that there are going to be some formal charges that are now on this molecule. All right, notice here every atom is neutral. All right, but once that bond is formed, you'll notice that there are now 4 electrons. If we mentally broke the bonds that are around that boron, there would be 4 electrons around it, and we know that it needs 3 in order to be neutral. So therefore, that puts a formal charge of negative on that boron. All right. Same thing with this nitrogen. It would have 4 electrons around it, but it needs 5 in order to be neutral, and therefore it's going to have a positive formal charge. All right. So one thing that so according to these definitions, notice what's going on. This particular chemical right here is the thing that is accepting an electron pair. It's accepting an electron pair from this chemical right here. So since it's an electron pair acceptor, it is a Lewis acid. All right. The electron pair donor is this one right here. That makes it a Lewis base. And one thing that I think that helps to remember the difference between acid and base here is to remember that a Lewis acid, you can make the argument, has more of a female role in this interaction, and the Lewis base would have more of a male role. So so one thing I want to point out is why Lewis acids do what they do. All right. So first of all, where do we find Lewis acids? Okay, so Lewis acids always tend to be fairly simple molecules, and they're always going to have either a central, generally they're going to have a central boron or aluminum atom in their center. And what's special about these is if you look at their position on the periodic table, you'll notice that they have 3 valence electrons. And the reason that that is important is that for both boron and aluminum to make neutral covalent compounds, they would only have 3 bonds to them. All right, so this is a neutral compound right here. But we also know about this thing called the octet rule, which says that molecules tend to be stable if their electrons have the same number of electrons as the closest noble gas. All right, so that would mean that boron would want to have 8 valence electrons around it, and right now it only has 6. All right, so in order for boron to have the full octet of electrons surrounding it, it would need to accept 2 electrons from somewhere. All right, so therefore, even though it's neutral here, in order for it to become stable, it wants to accept that one last pair of electrons, and that's why it acts the way it does. All right. All right. Last thing is I want to point out that this right here, this reaction right here, is reversible. So even though this is a relatively stable molecule right here, it is possible that these electrons that were donated could both go back to one of the atoms to regenerate the original compounds. Okay, so one thing that can be confusing about acid-base definitions is that the same compound could qualify by more than one definition. All right, so for example, if I were to show this particular reaction right here, well, you might take a look at the HCl and say, well, what's going on? Well, it looks like it's donating a hydrogen to water here. All right, and that's why the H2O now has H3O plus, and therefore that would make it a Bronsted-Lowry acid. All right, and that is absolutely correct. But you also might look at it and say, well, it's a hydrogen-containing compound, and it generates H3O plus when reacting with water. And by that definition, it would be what's considered an Arrhenius or an ionic acid. All right, and notice that both of those definitions end up coming up with the same conclusion, that this is acting as an acid. All right, neither of these are more correct than the other. They're just different ways of looking at something. All right, but once a chemical is correctly identified as an acid by one definition, it would never be considered a base by a different definition in that same reaction. All right, so notice that in this one, I'm only showing one particular reaction right here. And no matter how you looked at it, you ended up concluding that it was an acid. All right, you didn't say it was an acid by the Bronsted-Lowry and a base by the other. All right, so for example, if I show this particular reaction right here, this thing is only ever going to be considered base. All right, this can be a little bit confusing because that doesn't mean that this molecule right here can't be an acid. All right, so it's a base in this specific reaction. Right here I've shown the exact same chemical, all right, NH3, but I've just shown it in a different chemical reaction. And in this particular chemical reaction, it is acting, its role is changing. All right, here it was an acceptor of a hydrogen. Here it's going to be a donor of a hydrogen in this reaction. Therefore, in this reaction, it's acting as a Bronsted-Lowry acid. All right, notice it's not that it's inconsistent with this rule. It's just that you have to have 2 separate situations for it to be an acid in one and a base in the other. Okay, 2 words that are fairly important referring to acids and bases are amphoteric and amphiprotic. All right, so an amphoteric chemical is a chemical that could be an acid in one situation but a base in a different situation. And I just got done showing an example of an amphoteric compound. All right, in this situation, the NH3 was a base, but in a different situation, it was an acid. All right, so one of the world's most famous amphoteric compound is water. All right. So if you take water and you mix it with certain types of chemicals, specifically bases, in those situations, water is going to act to donate one of its protons, one of its H pluses. All right. Therefore, water would be acting as an acid in that particular role. All right. But if you take water and you mix it with a different chemical which tends to act as an acid, water is then going to act as an H plus acceptor. All right, noticing that in going from here to here, the H2O has accepted an H plus. All right, that's what makes it a base. All right, so that's what makes water amphoteric. That's a very, very important property about water. Just to use to make an analogy, you can say that salesmen are amphoteric because they're sellers in some situations and they're buyers in others. And what makes them a seller or a buyer, it depends on what you mix them with. If you mix a used car salesman with a buyer, they're going to act like a seller. In the same way, if you mix water with a base, it's going to act as an acid. If you mix it with an acid, it's going to act as a base. All right. So similar to that is what's called an amphoteric chemical. All right. And this is something that the IB curriculum requires that you know. An amphoteric chemical, it's similar to amphoteric, but it's a chemical that can accept or donate H pluses. All right, and because of that, if something could both accept or donate H pluses, then that means sometimes it would be acting as an acid and sometimes it would be acting as a base. So therefore, all amphoteric compounds are amphoteric. All right. But it's not necessarily true that all amphoteric compounds are amphoteric, all right? And I've only been able to find really one example of a compound that is amphoteric, it's amphoteric but not amphoteric, all right? And that is aluminum hydroxide, all right? So if I show this reaction right here, if you react it with water, it would dissolve and give some hydroxide ions when it's dissolved. So by that reaction, it would be acting as an Arrhenius base. All right. But if we take the exact same compound and instead of mixing it with water, we mix it with pure ammonia, which is NH3, this compound would end up acting as a Lewis acid. Remember, aluminum has got 3 valence electrons, so it's going to make a bond with 3 other atoms. And in order to satisfy the octet rule, it can accept an electron pair from something that has an available electron pair. And ammonia is the perfect chemical for that. All right. So notice that you have the 2 formal charges on the thing that you make. So note that this compound, though, is not capable of donating H pluses. All right. So it can't be amphoteric. All right, but since in certain situations it's acting as a base here and it's acting as an acid here, it would be considered amphoteric.